Math in the House. Today, we're doing Math in House, Chapter 1, Section 4, Fundamental Trigonometric Identities. I'm your host, Dr. D. Okay, so an identity in mathematics is a statement that is always true. And it can come from a definition. In this case, that's what it does. Sine of an angle equals opposite over hypotenuse. So if we have some point on a circle here, then we've got the x value and the y value of that point, and then the radius is going to be the hypotenuse of the triangle. So sine of theta equals y over r, opposite over hypotenuse. Then cosecant of theta is the reciprocal of that, r over y. Now, that gives us our first reciprocal identity, and that basically says that sine theta equals 1 over cosecant theta. It's just saying that sine and cosecant are reciprocals. And likewise then, cosecant theta equals 1 over sine theta. Now we can do the same thing with cosine and secant. Since cosine is x over r, and secant is r over x, then cosine and secant are reciprocals. In other words, cosine theta equals 1 over secant theta, and secant theta equals 1 over cosine theta. And then tangent theta equals 1 over cotangent theta, and cotangent theta equals 1 over tangent theta. These are the reciprocal identities. Now, the other identity we have here is from the Pythagorean theorem. We've got this right triangle, and so x squared plus y squared equals r squared. And that means that the radius is going to equal the square root of the quantity x squared plus y squared. Piece of cake. Okay, cruising onward. Now, we're going to take our Pythagorean theorem to start with. X squared plus y squared equals r squared. And we're going to manipulate it algebraically to end up with a trigonometric identity that will be enormously important. Okay, so if x squared plus y squared equals r squared, what I'm going to do is I'm going to divide through by r squared. So now I have x squared over r squared. Well, x squared over r squared equals x over r quantity squared. And then y squared over r squared becomes y over r quantity squared. And of course, r squared over r squared equals 1. Now, if we go back to that unit circle, we realize that x divided by r is cosine theta, and y divided by r is sine theta. So what I have here is cosine theta plus, or cosine theta squared plus sine theta squared equals 1. And I can, well, one other thing we're going to look at here. Sine theta quantity squared. The way we notate this is sine squared theta. And that's the way you say it, sine squared theta. The reason is, if I wrote it like sine theta squared, then this would be the sine of the angle squared, not the sine of the angle squared. So if you want the sine function squared, then you write it sine squared theta. So basically what this gives us is a trigonometric identity that we call a Pythagorean identity because it comes from the Pythagorean theorem. And that is that sine squared theta plus cosine squared theta equals 1. Now, do you think that would be an important identity to memorize?
That's the smartest thing I've ever heard anyone say about anything.
Yes, I think we should memorize this. Okay. Now, if x squared plus y squared equals r squared, then that means I could subtract y from both sides, or y squared from both sides. So now I have r squared minus y squared equals x squared. Now this time, I'm going to divide through by x squared. So now I have r squared over x squared minus y squared over x squared equals x squared over x squared. So now r squared over x squared is r over x squared, and y squared over x squared is y over x squared, and then x squared over x squared is 1. Now, r over x is the reciprocal of cosine, so that makes secant. And y over x is tangent, so I have secant squared minus tangent squared equals 1. Secant squared minus tangent squared equals 1. Should we memorize this one? I think we should.
That's the smartest thing I've ever heard anyone say about anything.
Okay. Now, the next thing we're going to do is we're going to subtract x squared over to the right. So now I have r squared minus x squared equals y squared. Now I'm going to divide through by y squared. So now I have r squared over y squared, which is r over y quantity squared. X squared over y squared is x over y quantity squared. And y squared over y squared is 1. R over y is the reciprocal of sine, so that makes it cosecant. X over y is the reciprocal of tangent, that makes it cotangent. And 1. So, cosecant squared minus cotangent squared equals 1. Should we even memorize this one? I think we should.
That's the smartest thing I've ever heard anyone say about anything.
Okay. All right. So we have smart things to say here. Okay. Now, just to help you remember these, sine squared plus cosine squared equals 1. So all you do is link sine squared, cosine squared in your mind. Now, the order doesn't matter because there's a plus sign here. So if you like cosine squared plus sine squared equals 1, that's fine. Now, with the secant and the tangent, order does matter because there's a minus sign there. Oh no! Which order? Should it be secant or tangent first? Well, we have our English alphabet that puts S before T. So that's how you remember it. It's in alphabetic order. Secant squared minus tangent squared equals 1 because S comes before T. Now, the same thing with cosecant squared and cotangent squared, although you can't use the abbreviations, you have to use the entire word spelled out. But if you were to look up the word cosecant in the dictionary and cotangent in the dictionary, S comes before T. So cosecant squared minus cotangent squared is 1. And it's basically the same thing as this one, only with cos on the end. Now, you really do need to memorize these three identities because they're going to come in handy in the future exercises. Okay. So, when you take sine squared plus cosine squared equals 1, if I wanted to substitute a cosine squared for sine squared, all I do is subtract cosine squared from both sides. If I want to substitute a sine squared for cosine squared, all I do is subtract the sine squared from both sides. Now, the same thing can be done with the secant and the tangent. If I add the tangent to both sides, then I have secant squared equals tangent squared plus 1. If I subtract or let's say add the tangent squared and then subtract 1, I have tangent squared equals secant squared minus 1. And same thing with cosecant squared and cotangent squared. It's the exact same thing. Cosecant squared equals cotangent squared plus 1, and cotangent squared equals cosecant squared minus 1. Now, the reciprocal identities, if I take the fact that sine theta equals 1 over cosecant theta, if I multiply both sides by cosecant theta, then I have sine theta cosecant theta equals 1. And if I take the cosine and the secant, then I can do the same thing. If I take the tangent and cotangent, tangent times cotangent equals 1. So these are identities that we'll be able to use in trigonometric proofs. Trigonometric proofs? Yes. Okay. So, all right. Verifying trigonometric identities. The goal is to get the left side of the statement to match the right side of the statement. Now, the method is we substitute known identities for specific terms. And we just went over a bunch of known identities that we can use. Now, we could also change secant, cosecant, tangent, cotangent into sine and cosine. You know secant's 1 over cosine, you know cosecant's 1 over sine, you know tangent is sine over cosine, and cotangent is cosine over sine. You can multiply either side by a fraction that equals 1. So it could be any fraction where the top and the bottom are the same. Now, here's the key thing. You can work on the left side, or you can work on the right side. Or you could work on both sides, but you are never allowed to multiply or divide both sides by a given term. The reason is because we're asked to verify this identity. That means we're trying to prove that the left side and the right side are equal. So if we multiply both sides by some given term, then we're assuming that it is an equation, that you can multiply both sides by a given term. So that's called circular reasoning. You're trying to prove something, and so you're assuming that what you're trying to prove is already true. And you can't do that. Okay, so let's try some of these. We're being asked to prove that sine theta times the quantity cosecant theta minus sine theta equals cosine squared theta. Now, what we're going to do is work on the most complicated side and try to make it equal to the simple side. So I'm going to work on the left side and make it match the right side. Remember, I'm not allowed to multiply both sides by something because that's not an equal sign. That's an alleged equal sign. We're trying to prove it's actually an equal sign. Okay, so let's do this thing. So what we do is we multiply through the sine theta here. So I have sine theta times cosecant theta minus sine theta times sine theta equals cosine squared theta. Now I haven't touched the right side. Okay, next, I know that cosecant theta is 1 over sine theta. So basically, sine times cosecant equals 1. And sine theta times sine theta is sine squared theta. All right, so now 1 minus sine squared theta equals cosine squared theta. Now, we've already shown that that's true, but just in case there's any doubt, what I'm going to do is I'm going to change the, I'm going to say 1 equals sine squared theta plus cosine squared theta. So sine squared theta plus cosine squared theta minus sine squared theta. Remember, because sine squared theta plus cosine squared theta equals 1 is a Pythagorean identity that we have all memorized. So now look what I have. Sine squared theta minus sine squared theta, that's 0. So I end up with cosine squared theta equals cosine squared theta. That's it, QED. Now, QED is a Latin term, and it means, or it stands for quod erat demonstrandum, as was to be demonstrated. Now, this is a traditional thing that you write at the end of every proof. It simply means I did what I was asked to do, that's it, I'm done. But knowing mathematicians, there is a certain level of arrogance with mathematicians, and so QED has associated with it that arrogance, like I did it and you couldn't do it, so I'm cool. So that's really what goes in there. Although a lot of mathematicians will deny that arrogance and just say, well, it's something we just do to put at the bottom of a proof to know that the proof is complete. So you could look at it either way. So let's try another one. Cotangent squared times secant squared minus cotangent squared equals 1. Okay, now, the first thing that I see to do here is factor out a cotangent squared. So we have cotangent squared times the quantity secant squared minus 1. Now, remember, secant squared minus tangent squared equals 1. That's a trigonometric identity that we've all memorized. So if I add the tangent squared over to the right and I subtract 1, then I end up with secant squared theta minus the 1 equals the tangent squared theta. So what I can do is I can substitute the tangent squared theta in here for secant squared minus 1. All right, now what I have is cotangent squared. This really is finished at this point, but just to make sure it's completely clear, cotangent squared is cotangent times cotangent. And tangent squared is tangent times tangent. All right, now we have the commutative property of multiplication that says I can change the order anywhere I want. So I can take a tangent times a cotangent times a tangent times a cotangent. Now, we know that tangent theta equals 1 over cotangent theta. So we also know then that tangent theta times cotangent theta equals 1. So basically I have 1 times 1 equals 1. So 1 equals 1, that's it, QED. So these are fairly simple at this point, and they get a little more complicated, but the key thing you need to know is your Pythagorean identities. Okay. All right, sine theta minus cosine theta quantity squared equals 1 minus 2 sine theta cosine theta. All right, now we have to remember some algebra. Remember algebra? Yes. Okay, so we know that A minus B quantity squared equals A squared minus 2AB plus B squared. So that's what we're going to do here. We have A squared minus 2AB plus B squared. Now, the temptation is to say, well, let's just add 2 sine theta cosine theta to both sides and they'll cancel out. You can't do that because this is not an equation. We're trying to prove it's an equation. So what we want to do is we want to put this, we'll just use the commutative property of addition here and put the sine squared theta plus cosine squared theta minus 2 sine theta cosine theta equals 1 minus 2 sine theta cosine theta. Now, sine squared plus cosine squared equals 1. So notice the left and the right side match. Our job is done here. Okay, so basically what we've just had here are some examples of using trig identities to verify other identities. All right, now, how do we write the cosine function in terms of the tangent function? Okay, so we know that cosine squared equals 1 minus sine squared. Okay, so now we want to be able to write one trig function in terms of another. For example, write, well, the cosine function in terms of the tangent function. Now, if I was going to do the cosine function in terms of the sine function, then I would use cosine squared plus sine squared equals 1. But now cosine and tangent, I don't have an identity that has the cosine and the tangent together. But what I do have is the identity that says that secant squared theta minus tangent squared theta equals 1. Now, the secant is the reciprocal of the cosine. So in other words, I could write this 1 over cosine squared theta minus tangent squared theta equals 1. Now all we have to do is take this and get cosine alone. All right, so how do we do that? Well, we'll add the tangent squared to both sides. So 1 over cosine squared theta equals tangent squared theta plus 1. And now we want to reciprocate both sides to get cosine squared theta alone. And finally, we take the square root of both sides. So cosine theta now equals plus or minus the square root of 1 over tangent squared theta plus 1. That's it, game over. Notice we have cosine in terms of tangent. Okay, so cruising onward. Now we're given that cotangent theta equals negative 9/40 and theta is in quadrant 4. So we want the other 5 trig functions. Okay, so let's look at cotangent theta. Basically, we know that it's x over y equals negative 9/40. So if I draw that picture, basically what I'm saying is x is negative 9 and y is 40. So it could be up here, negative 9 and 40. There's a negative 9 to 40 ratio. It also could be down here, where I have a 9 and a negative 40. And when I go x divided by y, I have 9 divided by negative 40, which is negative 9/40. So notice they're saying it's in quadrant 4. So the one in quadrant 2 is not the one we're interested in. So we're interested in this one here. Now, what is our hypotenuse? Because if we want all 5 trig functions, then we need to know what that hypotenuse is. So we could use the Pythagorean theorem. We could say 9 squared plus 40 squared equals r squared. So 9 squared is 81, 40 squared is 1600. So r equals the square root of 1681, which ends up equaling 41. So r is 41. And that is a Pythagorean identity that, or I mean a Pythagorean triple that is handy to know. 9, 40, 41. Okay, so we now can get all the trig functions. Notice here's my theta right here. So sine theta is opposite over hypotenuse, which remember this is 41, and so it becomes negative 40 over 41. Cosine theta is adjacent over hypotenuse, which is 9 over 41. Tangent theta is naturally the reciprocal of cotangent, so that's negative 40 over 9. And then cosecant theta is the reciprocal of sine, so that's negative 41 over 40. Secant theta is the reciprocal of cosine, so that's going to be 41 over 9. And we were given cotangent theta is negative 9 over 40. Now, check one more thing. Notice sine is negative. Why? Because the triangle is down. That makes sine negative. Cosine is positive. Why? Because the triangle is to the right, so that makes cosine positive. And tangent is negative because it's in the fourth quadrant where sine is negative and cosine is positive, so tangent has to be negative. So that's it. Have fun with these.
That's all, folks.